Hello and welcome to another Dyrobes modeling example. This screencast will be a walkthrough of the Whirlspeed stability analysis. This analysis is also sometimes referred to as an eigenvalue analysis. For this analysis, we're going to use an example that ships with most distributions of Dyrobes. This is the ch_a_air compressor_linear.rot model. It is a small gear-driven air compressor. All right, so the first thing we need to do is get Dyrobes started. This is the little screen that pops up when you start Dyrobes 18. So to get things started, we press rotor for rotordynamics, and that'll bring up the Dyrobes rotor code. This is the code that we use for doing most all of our modeling for lateral analysis. The other versions of Dyrobes look very, very similar, and the process is very much the same. A few slight changes here and there, but I think this will help you even if you're not using version 18. To get started, what we'll do is we'll load up this example. Again, this example can be found in the Dyrobes examples directory, which is usually installed in the same directory as the Dyrobes code. So this is the model we're going to work with. This is a small gear-driven air compressor. So to get started, let's review the model. So the place the model data lives is in the model data, the place that the model data lives is in the model data editor. So let's open up the data editor. The first tab that we see is the unit's description tab. This tab gives us a place to put some descriptive text to describe the model that we are creating or working with. This I find to be extremely helpful. I can never remember a few months down the road what on earth I was modeling, so I always try and put something here to remind myself. The other thing that shows up here is the system of units. The system of units is extremely important to have it match what you think it's going to be. In this case, we're using engineering English, so seconds, inches, pounds, force, pounds, mass. If you have the wrong set of units here, you're likely to get results that are really weird and strange, and this is a good place to look if you get weird and strange results. The second tab is the materials tab. This is where we define our materials. So in this case, there are 4 materials defined for various different parts of the model. The next tab is the shaft elements. This is where we define the geometry of the model. This model has some advanced features. It's using layers, multi-layered elements that we can talk about on another screencast. There are no disks. There are a couple of unbalances defined. We talk a little bit about this in the screencast on unbalanced response. The thing to note here is that unbalances are defined in terms of elements, not stations. So you have an unbalance on element 5, and you have an unbalance at the left end and the right end. So something important to remember that that's actually how those are defined. The bearings are defined on the bearings tab. In this case, we're using bearing coefficients from a data file. So these are bearing coefficients that we're going to generate using bperf, and they come out of bperf as a data file. If you have trouble running this example after you've created the bearings, which we'll do in just a moment, the most likely problem is that you have the wrong path to those BRG files. So you would simply browse to where you think those actually are and fix that, and that should make your example run. And that is all that we have in this model. So we'll go ahead and close this data editor. We didn't change anything, so we don't need to change anything. So what we're going to do next is we're going to go over to the bearing code, which in Dyrobes 18 you start from that same little set of windows. And I'll show you how we generated those .brg files. Some distributions ship with them, I think, and some do not. So we would go and open the 2 files. I've already opened up recently, so they're in my recent files, but certainly could also go open fixed lobe dimensional file. That should bring them up, and they're .ldi files. So to run these, we go to fixed lobe dimensional analysis, click on that option. We'll talk about bearings in another screencast, but for the moment all that data is good, so all we need to do is run it. Runs very quick. It generates a little text file that has summary information that describes how the analysis went. That doesn't help us out in this case, so we've run it. The next thing we do is go to the post processor for the fixed lobe or fixed geometry bearings. The last option there is to output stiffness and damping coefficients for Dyrobes rotor. This generates the .brg file, which is a text file that has the bearing information in it that Dyrobes is expecting, and that it's in the right format and all that good sort of stuff. So we just go ahead and click OK here. We then repeat the process for the other bearing, fixed lobe, dimensional analysis. We run it. It runs very quick. We close that, and then we go over to there, and we're going to do an output of the bearing coefficients. And that will create the .brg files that we would like, that Dyrobes is needing. So now we're pretty much ready to run. And to run an analysis, we go to the analysis menu. And from the analysis menu, we'll pick lateral vibration, since we're going to be doing a lateral analysis. And we're going to be running the Whirlspeed and stability analysis. There's a number of different analyses that we can run, so this is where you pick them from. This analysis setup dialog is set up into a group of boxes, different sort of boxes that go to different types of analysis. The first box up here is common across all the analyses. It gives you some shaft element effects, which you would want to have rotary inertia, shear deformation, and gyroscopic on. You need those to get the right answer. G sub Z is a setup to let you do vertical shafts so that the gravity is applied in the vertical direction. Something I'll point out is if you ever are working in Dyrobes and you wonder about something, on a lot of the screens you can hit F1, so I'll tap F1, and that'll bring up context-sensitive help, which can help explain what it is that Dyrobes is expecting you to do or explain some of the parameters. There also is a help button down at the bottom on a number of the screens that does the same thing. If you're using Windows 7 or 8, I think, probably 10 as well, and you have an older version of Dyrobes, particularly version 17 and earlier, to get that help system to work, you'll need to download a driver from Microsoft. It's the old style help, and it's well worth the kind of pain of getting that driver installed and getting the old style help working, because the help screens are extremely useful for trying to figure out what Dyrobes wants you to do or is asking you to do. To set up our Whirlspeed and stability analysis, we'll go down to this box called Whirlspeed and stability. We need to enter a starting speed, an ending speed, and an increment. The Whirlspeed analysis solves for the eigenvalues, or the damped whirl speeds, at a set of speeds. So this sets up which speeds you do. And finally, how many modes you'd like to solve for. 6 is a pretty good answer there. So we then click Run, and that pops up a little window that runs fairly quickly. We then go to post-process it, so we go to the post-processor option, Whirlspeed and stability. This brings up a box that has a set of options. First option is text, which gives detailed results. It's usually not where I would start, but if you needed to look into some of the actual numeric details of the results, this is a good place to go. It also, if something doesn't work right, can be a helpful place to go sometimes and debug things. First thing we'll look at is the Whirlspeed map. This is a graphical presentation of how the natural frequencies of that system change as a function of speed. And these are the changes due to gyroscopic effects and to the speed-dependent bearings that we have in there. It defaults to the first 4 modes, which you can see here, mode 1, 2, 3, and 4. It also defaults to showing a 1x line, this orange line, reddish-orange line here. The intersections between that line and the mode lines are an estimate of your damped critical speed, which is generally pretty close to where you see the critical speed peak, although in rotordynamic systems, sometimes we have very heavily damped systems where there is some difference between that intersection and where the peak actually occurs. A lot of plots have options to change some of the things on them, to customize them a little bit. So what we're going to do is we're going to say, let's look at all 6 modes. Let's put an operating speed reference line on that plot. So 35,000 RPM is where this thing claims it runs. And then I'm going to click the curve fit option to show you an issue with the Whirlspeed map that sometimes can make it a little bit confusing to figure out what's going on. So there we have it. We've now got 6 modes, 1, 2, 3, 4, 5, 6. We've got a reference line at 35,000 RPM, which is our running frequency, to give us some sense of how running speed relates to these modes. The other thing you can see now is that you've got these lines that jump back and forth. What the curve fit option does is it connects the little dots, the speed points that we calculated at by mode number. So this is all mode number 6. At this point here, at around 32,000 RPM or so, 31,000 RPM, another mode comes into being. So there's a mode that's this mode here. It drops down to 0 at just around that speed. So above 32,000, this becomes mode 1 instead of that, which means that this is no longer mode number 6. That's now mode number 6. And a similar thing occurs at this intersection here where this line suddenly appears to be jumping between the modes. So the curve fit option is kind of easy to get confused with some rotor systems, with many rotor systems, that have this characteristic of a mode either appearing or disappearing at some speed in the analysis. So that's why it's sometimes actually much nicer just to run this analysis with a fairly tight speed spacing. That works really well in smaller models. If you have a really, really big model, that tends to take a while to run depending on how fast your computer is. So a lot of times we'll leave that curve fit turned off. And your eye does a pretty good job of connecting the various modes that need to be connected. So that's the whirl speed plot, tells you where the damp critical speeds might be. Another post-processor for whirl speed stability is the stability map. This plots a stability parameter. In this case, we've chosen to plot log decrement, that's the default, as a function of speed. So log decrement, if it goes negative, that predicts an unstable, rotordynamically unstable system. So what we would examine is this is for places where the log decrement goes negative. This plot, again, if you customize it a little bit, works out a little bit easier for you. So we'll add a speed line. And then the other thing we'll change is go to manual scaling. So if we go to set a max Y value or log dec of 2, this plot's going to work out a little bit better. This is also where if you don't like log decrement, if your calibrated thinking is to damping factor, you can change from log decrement to damping factor in this option. You can also set that as a global option in the preferences. So there we go. That's a little bit more meaningful stability plot. It shows you that as a function of speed, there is a mode that is steadily decreasing stability. And in fact, if you ran this analysis for a higher speed range, if you ran this up to say 70,000 RPM, you would find that this mode right here, this least stability mode, will go across the threshold at around 60,000 RPM. It doesn't necessarily mean that's the second mode. That's the mode with the lowest stability, or first or second mode. These are the lowest with stability. If we want to find out which mode that is, or we want to find out a little bit more about the modes, the other plot that I use quite frequently is the 3D processional mode plot. This plot shows you the mode shape, or the mode shape of that particular mode at that speed. So if we wanted to go look at something at around 50,000 RPM, which is the highest speed that we ran, we see the first mode there, and we can animate these to sort of help us see what's going on. In these mode shaped plots, clockwise motion is backward whirl. So this is a backward whirling mode. The next mode up is a forward whirling mode. And then likewise on up as we go. And if we look at the detailed information on this, this says that our damp natural frequency here is 25,000 RPM, or 25,000 CPM, at a shaft rotational speed of 50,000 RPM. And the log decrement, which is our stability parameter, is 0.1488. This is the mode that does go unstable, I'm pretty sure. But to confirm this, if you ran this with a wider speed range, you could then go back and figure out which mode it is that goes unstable. So that is how those options work. All right, the other thing I wanted to show you in this screencast was how I generally get these plots into, say, Word. You'll notice there's a print to file option over here in the options. That will save the file to a PNG or a JPEG or something like that, a graphic file, which you could then import into Word. Unfortunately, you can't do a direct cut and paste of this. Dyrobes doesn't do that. But what you can do is if you select this window and then hit Alt print screen. So hold down the Alt button and type and hit the print screen button at the same time. That'll do a screen copy of the active window. And this is the active window. If we then go to Word and then we paste that in, we will get that complete window. That's usually not what you want to show in your reports. So if we click on that and we figure out where Word has hidden the crop option, which in this case is hidden in this little window, or this little menu option, we can take that plot, we can crop it a little bit. Oops, come on. Yeah. And you may have to tweak it a little bit to get it all to work out really well, but you can then get a plot that doesn't show that extra stuff, and that's how I frequently get Dyrobes plots into Word, is by using that Alt print screen and paste option. Works pretty well. It's almost as quick as just a simple Control-C kind of cut-paste. So that's how you run a whirl speed analysis and eigenvalue analysis using Dyrobes.